centripetal acceleration and centripetal force. In the last video, where we saw the motorcycle going around the different turns, we explained the centripetal acceleration equation, where if the speed is increased, the acceleration actually increases as the square of the speed. So if you double the speed and keep the radius the same, the acceleration actually goes up 4 times. And so the acceleration would increase dramatically. We also saw that if the turn got more gradual, in other words, if the radius got larger and larger, the acceleration got smaller and smaller. And both of these are intuitive, because if you go around a tight turn at a particular speed, you feel it more than if you go around a gradual turn. Likewise, if you go around a turn faster, you feel more than when you go around a turn slower. Again, the speed has a doubling effect because you're not only doubling how much you change your direction than you would if you were going at a slower speed, but you also double the speed itself. So that's why a directional change and also a speed change causes the doubling effect for the overall acceleration. Cars go around corners. Roller coasters go around turns and around circular paths here. Jet aircraft bank and make turns. And there are so many other things that spin and turn. So how do we use our centripetal acceleration equation to calculate all of this spinning and turning? So we have an object here, and it's out 5 meters away from the center of the circular path that it's on, and it's going at 3 meters per second. So our knowns here are the speed and the radius, and we're trying to find the acceleration, and so we use our acceleration equation, and this is simply plugging in. So 3 squared is 9 meters squared over second squared divided by 5 meters. One of these meters cancels here, and we get 1.8 meters per second squared. So that's how you do problems for centripetal acceleration. So pause the video and put this slide in your notes, please. We've seen how to use our centripetal acceleration equation, but there is one problem. When we're looking at things like planets, we don't actually know their speed. We could calculate their speed using 2 pi r over the period, but what we typically know about a planet is its period of rotation. When we use telescopes and triangulation, we could find out what its period of rotation is about the sun, and we could also figure out its radius of orbit about the sun. So since we know the radius and the period, it might be nice just to find a centripetal acceleration equation in terms of period and radius. And that's what we're going to do next. So let's look at another way to calculate centripetal acceleration. What if we had a situation here, like the planets, where we had a planet orbiting? Of course, this isn't a planet because this is not very far away. But let's say that we have an object going around in a circular path, and we know how long it takes to get around, and we know what the radius is. Could we find another equation that can tell us centripetal acceleration just based on those two variables? So if we start here with our centripetal acceleration equation, v squared over r, but in place of the v here, we plug in our circular motion speed equation, 2 pi r, the circumference over the period. I plug that in for v right here. So all of that got plugged in for v. And all of that needs to be squared. So 2 squared is 4, then we have pi squared, then we have r squared, and then we have the period squared. But notice that the radius down here will cancel one of the radii up here and cancel that square. And so we do get another equation for centripetal acceleration. it looks a little bit more cumbersome, 4 pi squared r over the period squared. And we get it by exercising our two previous equations. You really could just solve for v first and then plug it in here and do it as a two-step problem. Or you can just start with this equation and it'll work just fine if these are your two knowns. So pause and note all of this. So let's practice. Let's take note of how we use this new centripetal acceleration equation. And again, here's our situation where we have a radius of 3 meters and a period of 4 seconds. And we want to know that centripetal acceleration. So since we know r in the capital T, this is the equation that we grab. And using that equation here, plugging in 4 times pi squared times the radius, and then all divided by the period squared, plugging all of that in, and we would end up with 7.4 meters per second per second. So note this in your notes to show you how you can exercise this centripetal acceleration equation. And now for centripetal force. And when you are moving around in circles, you can experience some pretty extreme forces. As much fun as that looked like, I don't know if I could take that. Anyway, I'm more suited for analyzing what's going on in a jet aircraft. So we know about centripetal acceleration now, and to get to centripetal force and what's really causing these centripetal accelerations we've been working with, it's really quite easy. We go back to Newton's second law, and Newton's second law, remember, is just F equals ma. There is one tiny difference though. We put a little c here to call it centripetal force, and we put a little c here to call it centripetal acceleration. And that's key because this force, centripetal force, does not cause a change in speed. This centripetal force causes only a change in direction. So since it's only causing a change in direction, we have to note it as something special here. It's only causing a change in direction. We call it centripetal force and centripetal acceleration. So that's our first centripetal force equation, just F equals ma. That's a simple one. And if we plug in our two centripetal acceleration formulas right here, we can derive the other two forms for centripetal force. So in other words, centripetal acceleration is v squared over r. Plugging that in, we can see that we can calculate centripetal force with this equation, mv squared over r. And we had this bigger, more complex centripetal acceleration equation. So when we plug that in here, we get this centripetal force equation. Again, this one is good when you have planetary motion and that kind of thing, where you only know the radius of the orbit and the period of the orbit. So those are our centripetal force equations. And this one by far is the most used, the mv squared over r. But you're going to want to note all of this before moving on. So let's look at a common type of a problem with centripetal force. We have our object here with a mass of 0.6 kilograms. It is cruising around this circular path with a constant speed of 6 meters per second, and this circular path has a radius of 4 meters. So those are our three knowns. Those being the three knowns, and we want to find out what our centripetal force is here. We label or note our knowns, and the equation that makes sense, since I know the mass, the speed, and the radius, would be our centripetal force equation, mv squared over r. And so this is then just a straight plug-in problem, putting in all the knowns, remembering to square the 6 meters per second and then cranking it out and getting 5.4 newtons. So pause this and record this information. We have a couple last details here. One is to talk about the direction of the centripetal force vector. Well, that should become quite obvious here by its name. Centripetal means toward the center. And it should also be obvious that it's toward the center because it is what's causing the centripetal acceleration. So they should be in line with each other. And we finally know why objects move in a circular path is because they're getting pulled or pushed toward the center of the circle with this centripetal force. So when you draw these vectors on a diagram, you usually draw them different sizes because you also have the mass which is scaling them, and so they wouldn't be the same size. You can either draw the centripetal force bigger or smaller, but typically don't draw them the same size. But they both would be directed toward the center. Make sure you note that. And finally, overall force. Centripetal force, if you recall, is only toward the center. And centripetal force is what keeps an object going in its circular path. And up till now, we've just been talking about uniform circular motion, objects moving at a constant speed while they're going around a corner. But we know that it is possible to speed up or slow down while you're going around a circular path. So what's happening there? Well, let's take a look here at our first position. We would have a centripetal force, which is responsible for changing the direction, and then we would have another force, which would be speeding up. Let's say we have a car. The wheels, how much you're turning the steering wheel, would direct the centripetal force because there would be a certain amount of friction that's pushing the car in its circular path when you turn the wheels. Then you would have the accelerator in a car that you would be pressing on if you wanted to speed the car up. So the wheels with the frictional force pushes it in, and the wheels turning drives it forward, and it causes it to accelerate going forward. So what we would see a little while later here is that the car's speed would have picked up. Of course, if the car's speed picked up because it's accelerating, because you're applying the gas in the gas pedal, you also must be increasing the centripetal force here because obviously the tires have to work harder with friction to push the car toward the center because it's going faster. And we know that if we increase the speed, the acceleration is going to increase because we would need a much bigger force to hold the car going inward with that faster speed. So see if all of that makes sense to you. But again, centripetal just means toward the center, and in order to speed up or slow down, we would have to have an additional force acting. So this is a great one to add to your notes, and that'll pretty much wrap up our video here. And Scratch's parting questions. And good luck on your quest for continuous improvement.